And I hope you can all hear me online as well. So great. Thank you for joining us today for the HJAC talk after the winter break. I'm very happy to introduce Ilse De Looze. So let me find my notes with her CV. So Ilse did her PhD in Ghent, finishing in 2012. She then did a postdoc there where as part of that, she did a one-year trip to Cambridge that was followed by another postdoc position at UCL. In 2018, she came back to Ghent as an FWO fellow. And in 2020, she was awarded an ERC starting grant and took on a professorship there at the University of Ghent as well. So on your Twitter profile, it says you love everything about dust. And so I hope we will hear a lot about that today.
Thanks a lot. Thanks a lot for the introduction. I hope you all had a great Christmas break and a great start of the new year. So during my talk today, I'll cover a wide range of topics, but as a common thread, the origin of interstellar dust. So let me briefly introduce what dust is. Is this causing my sweater probably? I'll do something like this. So is it better? I'll try to move as little as possible. Okay, so I'm sure you're all familiar with the interstellar medium, which is the space in between stars, and which is made up of low density gas and microscopic dust particles. No, too much noise. Is it better? But can you still hear me at the back? Yeah, okay. So if you look at it by mass, the composition of the ISM is about 70% of hydrogen, 28% of helium, a few percentages of heavier elements, and about 1% of interstellar dust, which are basically solid particles made from metals. Now, if you look specifically at the dust composition, it's mostly made out of carbon grains and silicate grains, but also some other elements are depleted onto dust grains, such as magnesium, oxygen, and iron. And if we look at the sizes, which you can see on the figure here, it really ranges over almost 3 orders of magnitudes. So sizes go from below 1 nanometer to up to almost 1 micrometer. And if you imagine that's really, really small, if we look at the typical thickness of a human hair, which is about 50 to 70 micron, imagine dust grains, which are all smaller than 1 micron. They're very, very tiny. And even though they're so tiny and small in mass, they're very, very important. I also want to briefly outline the very smallest dust grains, which are polycyclic aromatic hydrocarbons. So it's these type of aromatic carbon rings with hydrogens attached to it. And even though they're very small, they're the smallest grains, they're very important. And I'll get back to them later in my talk as well. So why should we care about dust if it's such a small mass fraction of the ISM? Well, we know dust is obscuring a lot of stellar light. Up to 50% of all stellar light in the universe is obscured by dust grains. And specifically, if we look at young stars, they're almost all embedded in their birth cloud. So almost 90 to 99% to 100% of the starlight will be obscured by dust. We also know that dust grains are efficient coolants. So they can enhance star formation, so they can enhance the collapse of clouds and enhance star formation in this way. We also know that the surfaces of dust grains are very important. They provide a site for atoms to meet and for molecules to form. In such a way, molecular hydrogen can form very efficiently, which is, of course, the fuel for future star formation. And then we also know that dust grains can potentially play a role in radiation pressure on dust grains that can drive outflows. And I'll get back to this later on as well in my talk as well, specifically on how we can use dust grains to trace dusty outflows. So knowing the origin of dust and understanding the properties of dust is very important. First of all, is if we want to simulate correctly how star formation proceeds, how different molecules form in the ISM, we need to understand the grain size distribution, the properties of dust grains. And also if we want to derive accurate star formation rates, stellar masses, etc., from observations, we need to correct for dust obscuration, which is very important. Now, let's have a look where all this dust comes from in the ISM. there are various dust sources. So first of all, we have the stellar sources, which are known dust producers. So we know that low and intermediate mass stars on their asymptotic giant branch produce dust in their circumstellar envelopes here, in the dusty envelopes. We also know that massive stars produce quite a lot of dust after they went supernova. So in the ejecta of the supernova remnants, in the remainders, dust grains can condense when everything has cooled down sufficiently. And then there's a non-stellar dust production source, which is grain growth. So it's supposed that we have some grain seeds that are present from the stellar production sources, and that we also have some elements which are going to accrete in dense regions of the ISM to form bigger grains. So this is a mechanism that is not well understood yet, and I'll get back to exactly why that's the case, why it's not that well understood yet. Then if we look at the dust destruction sources, two main dust destruction sources are, first of all, simply astration. You have a molecular cloud, parts of the cloud are collapsing to form new stars, which are incorporating dust grains and metals into these new stars. And then, of course, a very important dust destruction source are the supernova shocks. So they're both destroying pre-existing circumstellar and interstellar dust, and I'll get back to that later on in my talk as well. So if we look at the life cycle of interstellar dust, we start from dust in molecular clouds. Stars are forming, so astration, where we're incorporating some of that dust into new stars. We have the low mass stars, which go onto the asymptotic giant branch, form some new dust particles. Then we have the high mass stars, which go supernova at the end of their lifetime, and also can form dust grains in the expanding ejecta afterwards, after the explosion. We have the grain seeds that eventually can grow bigger through grain growth. So what we know is that typically the dust's contribution from the dust that is formed in AGB stars is quite low if we look at typical star-forming galaxies. The contribution from dust that is produced in supernova is more significant. Typically per single supernova, around 0.4 to 1 solar mass of dust can form. But yet, if we then compare, each single supernova also has a lot of energy that is released into the interstellar medium, creating a shock wave that is expanding, and it is sweeping up a lot of material. Hundreds of solar masses of gas and dust is being swept up and is also destroying a lot of dust. So simulations show that a single supernova can destroy up to 70 solar masses of dust. Of course, if you do the maths, you very quickly see that currently we believe that supernova are net dust destroyers. And that's why we need another source of dust production. And that's where grain growth comes in. And especially if we look at galaxies at high redshift, it's very puzzling that they show such large masses of dust. And I'll get back to that at the end of my talk. Now, very briefly, before delving into the science, I want to show you this picture of supernova and supernova shocks. So you have your progenitor star, which is at the end of its lifetime. When you have iron in its core, it's gonna cause a supernova explosion. All of the material in the progenitor star is expanding, is moving at humongous velocities, 10,000 kilometers per second away from the explosion center. You get a forward shock, so the supernova blast wave here. And here is some circumstellar medium, which was lost by the progenitor star prior to explosion. Eventually, what will happen is you have this expanding supernova ejecta that is meeting here, the circumstellar medium, and you get a contact discontinuity between the ejecta and the circumstellar medium. So it's actually a separation between two very different fluids. What is happening? You get a forward shock that is propagating through the circumstellar medium. So you get a layer here of shocked circumstellar material. If there's enough mass here, what you'll get here is also a reverse shock. So at the contact discontinuity, you'll get a reverse shock that is now propagating inwards and can actually destroy a lot of the newly formed dust in the ejecta of supernova as well. So remember the 70 solar masses and the yield of a single supernova producing between 0.4 and 1 solar mass that may in the end be less because of the reverse shock processing. So I told you already that there is a problem. It seems stellar sources are insufficient to account for the observed dust masses in low and high redshift galaxies. And it seems grain growth is a required mechanism to produce the dust that we observe in galaxies today and looking back in the early universe. There are a few caveats to our knowledge, and I'll go over these 4 caveats in more detail during my talk. So I'll first talk about uncertain supernova dust yields. It's actually been not for that long that we realized that supernova are actually producing dust, especially supernova 1987A in the Large Magellanic Cloud has been a real game changer. For the first time, thanks to the combined efforts of Herschel and ALMA, we were able to detect the dust emission that is really coming from the supernova ejecta. And this has really set off way more observations to really follow and track supernova going off and trying to see whether they're dusty. The next source is Cassiopeia A. It's a very famous, well-studied galactic supernova remnant. The explosion dated back around 360 years ago. It was not seen at that time. You can see here, looking at the longer Spire Herschel wavelengths here, in the submillimeter wavelength range, there's a lot of interstellar medium in between us and Cassiopeia A. That's why back then they couldn't observe the supernova. And it's based on light echo spectra that they've been able to identify Cassiopeia A as a type 2b supernova, meaning that type 2b means, okay, at the time of explosion, the star has lost a lot of its hydrogen layer already. There was only a very tiny fraction of hydrogen left at the time of explosion, which was visible in the spectra. Putting that into numbers, progenitor mass was between 15-25 solar masses. What we observe in the supernova ejecta of this supernova remnant is around 4 solar masses. So the star has really lost a lot of its mass. Now, what we're interested right now is we want to see, okay, how much dust is actually present in those 4 solar masses of material that we know is present there. The main difficulty is, of course, if we want to model the dust emission from the supernova dust in the supernova remnant, is that we have to disentangle all the other emission components, the interstellar dust emission, synchrotron emission. Doing that in a rigorous way, in the end, we end up with this dust mass map that shows that most of the dust is located in the inner regions of Cassiopeia A, so within the reverse shock still, and we arrive at a total mass that ranges between 0.3, 0.6 solar masses. And this has later on been derived using independent dust mass estimates as well, finding very similar results for Cassiopeia A. And one such technique is not looking at dust emission, but looking at the dust obscuration effects that dust has. For instance, you can look at the gas that is expanding in supernova ejecta. For instance, we're looking at oxygen ions here. They're expanding. So normally, if there's no dust present, what you would expect is a sort of flat top profile. In this case, the dust-free model is not really a flat top just because there was a shift in asymmetry that was accounted for. But in an ideal situation, you would have a flat top model. If you incorporate dust in it, so you have dust formation in the supernova ejecta, the blue shifted photons here, material, the photons would just travel to us, whereas the red shifted part, photons would have to travel through the dust. And what you get is the red-blue line asymmetry. So the blue part is hardly affected, but the red side of the line profile is affected. Modeling that, you can actually get a very good idea of how much dust is present in supernova ejecta. And other than looking at the dust emission, the additional advantage that this technique has, it's insensitive, for instance, to the presence of any circumstellar dust, because the dust would be here and then would affect both blue shifted, red shifted sites in a similar way. So that's why it's a very promising technique, and applying this technique to a wide range of young supernova, you see that they actually follow a very similar trend. So you have a gradual buildup of supernova dust mass over 30 years' time, in the end reaching a plateau of around 0.42 solar masses, also very similar to what we observed for supernova 1987A. A very nice remark to make here is that actually models are quite divergent from the trend that we see in observations. What they show in models is that you get a very rapid formation of all dust grains out of the metals that are present in the first 2 to 3 years after the explosion. So there's definitely a discrepancy there. Potential explanation could be that indeed the dust is forming, but that it's optically thick and hence more difficult to detect, but that's still an open question for now. Then I want to turn to Casey and the observations that we did with the James Webb Space Telescope. So what you can see here is the mirror image. So let me walk you through what we're seeing here exactly. So in red and orange, what you're seeing is circumstellar material that is being shocked by the supernova blast wave. What we're seeing here in white, pinkish, is actually the main shell of reverse shocked material. So it's all ejecta, shrapnel, small clumps of material that remain from after the explosion that are now being hit by the reverse shock that is moving inwards. And then this green structure in the middle struck us in particular because it was a structure that we hadn't seen before. That was not detected before. It's detected in the central region. So we first thought, okay, this is some part of supernova ejecta material that wasn't seen before. Looking at the colors, it really peaks at 12.8 micron, as opposed to the red and orange that really peaks at around 25 micron. Now I just want to show as a comparison the Spitzer image that we have of this southwest part. Spitzer image, and then of the same field, even though it's the longest JWST filter here, you can see that there's an incredible increase in resolution and level of detail. And if you look carefully, this is actually the green monster here. There was a trace already in the Spitzer data as well. So looking back at the data, we can now identify the green monster there as well. Very briefly, before we turn to the green monster, this is the NIRCam image that we see with James Webb Space Telescope. Very different. What we're seeing actually now here is a lot of synchrotron radiation. So we know the forward shock here is impacting on circumstellar material that was lost by the progenitor star prior to explosion. And we see a lot of synchrotron radiation. And maybe you spotted this odd beast here as well. This is actually a light echo. Zooming in on it, this looks like this. So what is happening here, at the time of explosion, a lot of energy is released. A lot of photons are emitted. These photons have actually traveled 180 light years away from Casey, away from us, have heated up locally some cold, dusty material. That dust is being heated up, is re-emitting that energy, is traveling another 180 light years for us to detect this temporary light echo here. So we're seeing actually a lot of changes. If you have observations that are a few months apart, this light echo will disappear and you see other light echoes appearing. And this is actually a very interesting way to study the structure of the cold ISM. As you can see, it is a very peculiar structure. We don't know really where it comes from. It could be magnetic fields that shape the interstellar medium in this way. Now, looking also at the NIRCam images, something we can do, there's the 4.4 CO fundamental line, which is present in the 4.44 filter. We can make a JWST CO map if we subtract the synchrotron emission using other NIRCam filters. We also have near-spec spectra in two of the reverse shocked supernova ejecta regions, which you can see here. Zooming in on it, we can actually resolve, because of the huge or relatively large line widths of around 250 kilometers per second, we can resolve individual row vibrational transitions very nicely. And we can model this and we can derive the temperature of this and also the line widths, which suggests that the CO is likely coming from post-shock gas. So it's material in the supernova ejecta that has been hit by the reverse shock. And we're looking now at the post-shock gas where molecules are starting to reform. And this could also potentially be an avenue for dust to reform after reverse shock processing. Now, what's the green monster? What's the nature of the green monster? I'll show you a zoom in here. You can immediately tell there are a lot of peculiar structures, a lot of holes with rings around them. We were really baffled when we saw the images and didn't really know what we were looking at. There were a few clues. So we have one specific position where we have MIRI MRS spectroscopy observations with James Webb. So in this dusty ring structure that we observe here, we also see part of emission, part of the ring line emission originating from hydrogen, neon, and iron at relatively low radial velocities of around -50 kilometers per second. Of course, if we were to look at supernova ejecta material, this would be moving at thousands of kilometers per second. So this is a very low radial velocity. Also, the fact that we detect hydrogen, there shouldn't be any hydrogen left in the supernova ejecta. So we're likely looking at circumstellar material here. That's also confirmed because in black, this is an H-alpha image here. In black, we show optically identified dense shocked circumstellar clumps. And with dense, I mean 10 to the 3, 10 to the 4 per centimeter cubed. So really very dense regions. If we put the green monster structure on top of that, they seem to actually form a sort of coherent structure almost. Then finally, we also have analyzed X-ray data in a companion paper by Jaco Vink. So looking at various locations within the green monster and then looking at other regions where CSM material is present, we see a very nice correspondence. And we also see that all the X-ray emission in the green monster is consistently blue shifted. So this puts the green monster in front of Cassiopeia A, which means that it's been mass loss, that it has happened on one particular site. So putting that all together, green monster is circumstellar material. The James Webb images that you can see over here are not dominated by line emission, but it's really dominated by hot dust or warm dust with temperatures above 100 Kelvin. To reach these temperatures, it must be impacted by the forward shock. We observe a relatively low shock velocity. So this is actually inferred from the blue shifted velocities that we have inferred from the X-ray observations. You can derive a typical shock velocity of the forward shock moving towards us of around 3,500 kilometers per second. This is relatively low. So that must mean that the forward shock has significantly slowed down, meaning that there must be a lot of dense circumstellar material there. And that's also confirmed by the independent pre-shock density, electron density estimates that we have from the X-ray observation. So this is all suggesting that we have highly asymmetric, a dense mass loss phase. And this may re-invoke again the question of was there a binary or is there a binary companion to Cassiopeia A? Searches have not resulted in finding any companion, but could always be an alternative explanation. Either there was no binary companion, there was a merger event, or it could be strong convection cells that have really resulted in this one-sided mass loss. So the one thing that I still owe you an explanation about is all those different holes. So here you see, look at 4 different regions in different wavelengths. This is showing NIRCam, this is showing MIRI, and this is showing a narrow band filter where you can see the iron line emission. In particular, this region is very interesting. It almost seems like we're looking at different layers of circumstellar material where there's a hole being punched through the circumstellar layers. So we're quite confident that the holes that we're seeing are coming from an interaction between ejecta material and circumstellar material. However, the exact scenario is still up for debate. Option 1 is we know from observations, this is a paper by Rob Feasem from 2001, that there are a lot of high velocity ejecta knots that move ahead of the supernova blast wave. So they move faster. So they could have punched these holes in the green monster before the arrival of the supernova blast wave. That's one option. Alternatively, there are simulations done by Salvatore Orlando already before we knew of the existence of the green monster and its holes, where he shows that upon impact of the forward shock on the circumstellar medium, that you actually get hydrodynamical instabilities at the contact discontinuity, which cause, normally that's a region that cannot be penetrated because it's a separation between two very different fluids. But at the time, due to the instabilities, you get ejecta material that is actually moving through the contact discontinuity and is going to penetrate this shocked layer of CSM material. what you can see over here as well. So you really have ejecta material, these plumes here that are making holes in the layer of dense CSM material. Now, the way to differentiate between those observations is definitely new James Webb observations, because one difference would be that here, if in this scenario, we'd really expect to see ejecta material still somewhat present in those holes. Whereas in the first scenario, it's just an ejecta bullet that is making a hole and that is just moving on. So the final thing on the green monster. So how does the green monster differ from other CSM phases? So we've seen here, it's more red-orange in color in this multicolor mirror image. Here it's very green, the green monster. Well, it seems that both spectral energy distribution functions are fitted very well with a type of silicate grain, specifically these type of grains. So that seems quite similar. So the differences must be attributed either due to different grain heating mechanisms or different grain sizes. Now, the peculiar thing is what I mentioned or what I've shown before. You had these optically identified dense CSM knots. These were enriched in helium and nitrogen, indicating that they're really coming from the inner region of the hydrogen burning shell. So they really must correspond to one of the final phases of mass loss that the progenitor star has experienced. Now, normally in this CNO processed material that you would find there, normally you wouldn't expect very efficient formation of silicate grains, for instance. So there seems to be a contradiction. And hopefully, again, with silicates or with new James Webb observations of trying to derive also the helium abundances, nitrogen abundances for regions in the green monster, we can solve this puzzle. Now let me get on to the next caveat, which is about grain growth and whether it's viable. So the problem here is that we don't really know how grain growth takes place. Once we go in dense regions of the ISM, a V of 3 and higher, we're going to form ice mantles, and all the elements, gas phase elements that accrete onto this ice mantle, once your molecular clouds is dispersed, photodesorption will take place, and all the gas phase elements, everything you accreted is just returned to the gas phase. Looking at more translucent or diffuse ISM, there could be a potential explanation, but it seems in the models that were done by Svetlana Zhukovska that you really need a high abundance of small grains, because the very small grains will be negatively charged, so you get a Coulomb attraction between positive ions and negatively charged dust grains. Now, with some laboratory experiments that we performed, we did find some very promising prospects, not evidence of grain growth, but it does show that grain surfaces can be more reactive than we initially thought. And this is work done by a PhD student, Francesco Greco, in collaboration with François Dulieu at Lerma Laboratory in Cergy. So what he has done, he has actually done experiments in a ultra high vacuum chamber with interstellar dust analogs. In this case, we've used coronene as a PIH-like surface. We've had beams of hydrogen and oxygen that were aimed at interstellar dust analogs. And what we've seen is that water and molecular hydrogen is actually able to form on grain surfaces more efficiently than we thought before, so at very high temperatures. And this is actually only possible if hydrogen or oxygen is making a chemical bond with the layer of interstellar dust analog, so the coronene that we're using here. So this shows that there's actually, instead of physisorption, that you just have the van der Waals forces that provide the connection, that we have chemisorption, so really chemical bonds. So this provides a potential prospects for grain growth to take place as well. So now let's look at dust destruction. Have we overestimated it in the past? Just to give you an idea, there's really no consensus in the communities. This shows various papers with the dust destruction efficiencies that they've estimated. And this is the common consensus, which is none, as you can see. We've definitely made progress. Many studies have just assumed that the ISM is homogeneous, that you have a constant density, that you have a supernova going off in a constant ISM density medium. Of course, that's not the case. We know the ISM is highly inhomogeneous. You can have, if you have very different densities, for instance, your supernova shock will penetrate further in low density regions. And that's why we have to really model this inhomogeneous ISM. And the first effort was done by Florian Kirchschlager. As you can see, what they did is they created a multi-phase ISM by having 40 supernova explosions going off, creating a turbulent ISM in this way, then having one supernova explosion going off, and trying to see the comparison with how much dust is destroyed, the 70 solar masses in the case of the homogeneous ISM, and then the 60 solar masses in the case of the inhomogeneous ISM. So there is a little bit of a difference, but it's not a huge difference, as you can see. Now, within our group, we have a few new efforts underway as well. We're creating the turbulence in a slightly different way. So we have Fourier waves at different scales, different locations, to really create turbulence at the different levels of different scales. And we're doing that using the 3D magnetohydrodynamic AREPO code. In this case, I'm going to show you the results for a relatively high density case of 100 centimeter cubed. So a relatively turbulent molecular cloud. We model this with different density contrasts. So density contrasts meaning here we have the m equal to 0, which is the Mach number, shows you that we have a constant density. If we increase the Mach number, we get more turbulence. So you have higher density filaments and you have lower density voids. So there's a wider distribution in densities that we're observing. So this is work done by a PhD student, Tassilo Scheffler. We're not including dusts on the fly because that's too expensive. So we're doing it in post-processing. We're including the effects of transport of dust, gas, and plasma drag, magnetic fields, grain processing, such as sputtering, so collisions, as you can see, collisions with atoms or ions, electrons that are bombarding the grain and gradually eating away parts of the grain, destroying it in this way, or grain-grain collisions, which causes the fragmentation of larger grains into smaller grains. So this is all included. And then I'll show you the results of the simulations here. So this is the homogeneous case, which you can see here. And then over here, you see the other cases. You can see it's clearly we're ending up with a very peculiar shape also of the supernova remnants. So we're doing this up to about 10,000 years after the supernova explosion. So the speeds are still relatively high. The main results that we're actually seeing that the dust destruction efficiency, so in the different cases, it's best to focus on the solid lines. The solid lines both include sputtering and grain-grain collisions, which often work synergetically because sputtering is very efficient at destroying small grains, and the large grains are typically transferred to small grains by the grain collisions. So you can see the dust destruction is still quite efficient. We're still destroying quite a lot. For instance, in this case, in the first 10,000 years, we're destroying 10 solar masses of dust. So of course, this still needs to go on in a bigger box. And we also see that grain-grain collisions are actually very important. This is the synergetic effect that I just talked about. And in ongoing work, we're also doing this for lower densities and longer timescales. A similar effort, but on a smaller box, focusing on just one specific part, is being done by postdoc Nina Sartorio. So she's actually modeling simply a plane parallel shock front. You have a turbulent ISM, which is being hit by a shock front. And you can see here, this is actually the shocked CSM. So it seems some of the material here in these dense filaments is remaining there. The filaments are not destroyed by the supernova shock. We're also varying the shock velocities going from 1,000 to 6,000 kilometers per second. And we do this for an average density in this case, which is much lower of 6 per centimeter cubed. So what we see in this case, now we show the dust survival rate. So we start here as time progresses. So this is again for different Mach numbers. The black line shows the high density, the highest density contrast. So meaning that you have a lot of dense material in high density filaments. What we see here is that the dust survival rate is actually higher, So we're able to shield some of the dust in these high density filaments, which reduces the dust destruction efficiency. And of course, dust destruction is more efficient at high velocities. But the overarching conclusion that we have from those two studies is for now, that it seems that these density inhomogeneities, even though they can boost the dust survival rates by 20–30%, it's not going to make up, it's not going to bring our 70 solar mass of dust that is being destroyed down to a significantly lower number. Of course, I should say we've only been doing this for relatively high shock velocities. We also have to look at lower shock velocities where the effect of the shielding may be bigger. So that's something we still need to investigate. Then finally, I want to talk about the gaseous in and outflows and why they're important, and particularly how these polycyclic aromatic hydrocarbons, what I talked about in the beginning, these smallest carbonaceous dust grains, how they actually provide a unique tracer of the cool cloudlets that are entrained in galactic winds. So what you can see here is a beautiful image, Hubble image of M82, where we know they're feedback-driven outflows. And this is zooming in on this region with James Webb. And the red is what you see is our observations of these small hydrocarbon grains, these PIHs that we're observing. And the same here for NGC 891, which is an edge-on galaxy. So here we have James Webb observations in the optic or in the near infrared of the stars. And what we're observing here is the 7.7 micron, which is dominated by a PIH feature, where you can actually study the dusty extraplanar material in these dusty outflows. If I zoom in on this, so this is not the disk is somewhere located here, and this is the distance, so the vertical distance above the disk, then we see that we're detecting dust up to a scale height of around 4 kiloparsec. If you do the calculation and you assume that you have typical outflow velocities of around 50 to 75 kilometers per second, that must mean for these PIHs to reach the location here, they must have lived for about 50 to 80 million years, and that's quite long. Normally, if you would inject PIHs, these very small, almost molecule-like dust grains, into the circumgalactic medium, if they would be exposed to the harsh environments of this X-ray emitting CGM, circumgalactic medium, they should be destroyed in a few thousands of years. The fact that they're not destroyed must mean that this emission of the PIHs must come from cooler regions that are entrained in galactic winds. So this is actually a unique probe of trying to understand what is happening with the cool components of dusty outflows. And if you look carefully, we can actually observe a number of structures. So what we're seeing here, for instance, if you look carefully, it's also highlighted here, seems to be a feedback-driven superbubble. This was already detected on this side of NGC 891. Now we're also observing it here. Here there seems to be a smaller version of that, so all feedback-driven super bubbles that are sort of at the verge of bursting. Well, they have bursted out of the galaxy disk and could eventually develop into a full-blown galactic wind. What we're seeing as well, and that we're very much surprised about, and maybe you can see some of them as well, lots of clumps in these images. We've tried to identify them. At first we thought, okay, maybe it's background contamination, but then if you identify them with astrodendro, you quickly see that they're really located in the circumgalactic medium, because here you see a number of background sources, but the density of these background sources is sufficiently lower, significantly lower compared to here. Then if you zoom in, it seems all these clumps are okay, contrast is maybe not that great here, but you can tell here that a lot of these clumps actually seem to follow the trace of the filaments. So they're really located on these filaments, on these circumgalactic filaments, and on these feedback-driven outflows that we're detecting. Now, for the final 5 minutes of my talk, I want to talk briefly about dust in high-redshift galaxies and how we can try to understand how these large dust masses that we detect in high-redshift galaxies, how they've come to exist. ALMA has definitely been very revolutionary here. Before we were just picking up on the brightest targets, but now with ALMA, it's really possible to follow up even on sort of normal main sequence, normal star-forming galaxies at higher redshifts. And of course, there's a negative K correction that helps with that as well. So I'm going to briefly present a few results of a few ALMA large programs focused specifically on the results with regards to the dust properties and the dust specifics of these galaxies. First ALMA large program is REBELS, Reionization Area Bright Emission Line Survey. So it's a UV selected sample. So it's indicated in red here of 40 high redshift galaxies with redshift higher than 6.5. We've done spectral scans to infer the redshift, so detect C+ or O3. And we have C+ detections for 23 and dust continuum for 16 of these sources. So in this case, we are still somewhat biased because if you look at these surveys, we're somewhat biased to really detecting the brightest sources at these very high redshifts. The other ALMA large program is Crystal, which is C+ resolved ISM and star-forming galaxies with ALMA. In this case, we're operating at a redshift range between 4 and 6 when the age of the universe was about 1 gigayear. So it's beyond the epoch of cosmic reionization, but we're really tracing in this epoch the buildup of the first galaxies and how they grow to become really big galaxies. Now we know how we know them today. The advantage of Crystal is that it's a follow-up of previous spatially unresolved observations as done by the Alpine survey and pilot studies by the Peter Kapak paper in 2015. So we're actually able to spatially resolve C+ and dust emission at scales of around 1 kiloparsec in galaxies, only 1 gigayear in the age of the universe. So in brief, we actually started with around 19 main sequence galaxies, or here we should be probing somewhat the normal star-forming galaxies at the redshifts of 4 and 5. But we had more data from pilot studies and from what's available on the archive. So in total, we have 35 main sequence galaxies and 2 dusty star-forming galaxies. So all of them are main sequence galaxies, as you can see. Stellar mass is typically above 9.5. There are some with lower. And then all of them have HST, and a large fraction of these galaxies actually also have new James Webb observations, both near CAM and near SPEC. Now, the fact that we're spatially resolving these targets also means that we can study the kinematics and the dynamics of these galaxies. And actually looking at all of these sources, many of these sources in the spatially unresolved C+ observations seem to correspond to just a single blob, a single galaxy. Now spatially resolving all of these galaxies, we often see many blobs. So often there's evidence that we're actually looking at ongoing mergers of galaxies or multiple clumps within a single galaxy. So it's really worthwhile getting the high resolution to study all this kinematics. And this is work, ongoing work by Lillian Lee, which will soon be published as well. We also have a quite high detection rate for dust continuum. Now, for a few sources, we're also moving beyond the single data point because, of course, if you have C+, you have the dust continuum at 158 micron with one single data point of dust emission in the far infrared. You won't constrain dust mass and you won't constrain dust temperature at the same time. So for some sources, it seems we are able to trace the shape of the SED better with multiple data points. One such target is HC10. It's a crystal target as well. As you can see here, we find a peak temperature of around 36 and an SED temperature of around 46 Kelvin. Putting this on the dust temperature evolution diagram, what we can see, so up to a redshift of 4, there seems to be a gradual evolution, but this evolution now seems to level up because many high redshift targets seems to have somewhat of a lower dust temperature. And a similar trend is actually observed also in REBELS galaxies at higher redshifts of 6 and 7. What we're seeing here, so for these targets, as you can see here, we have 2 data points available, sometimes an upper limit. Again, the dust temperatures that we're deriving are mostly between 30, 35, 40 Kelvin, but again, quite low. I mean, I would expect quite a lot higher dust temperatures for these highly star-forming galaxies. Now, for this particular Rebels target, Rebels 25, which is the brightest galaxy, we have multiple SED data points, as you can see here. So we can really constrain the SED fairly well. We find a dust temperature of only 32 Kelvin on average, which is really low. And we also find a very peculiar dust emissivity index. So this is actually to constrain or to characterize the really gene scale here of the dust SED spectrum. Normally in the local universe, you find values between 1.5 and 2. Here there's a value of 2.5, which could potentially mean that there may be large grains due to coagulation or grain growth, but that's speculation for now. It's definitely unusual and very different from what we observe. Another explanation could also be that some of this dust is actually highly optically thick, because we often see, if you look at the James Webb images, HST data, ALMA data, the dust emission is coming from different regions than where the line emission and the starlight is coming from. Now, looking at the origin of dust and high redshift galaxies, what is producing most of the dust in these targets? So in this case, you were looking at the dust mass versus stellar mass. And what you can see here, so this is the fiducial model. It seems using dust production, dust destruction, and some amount of grain growth, it's possible to constrain the dust masses in these, or to reproduce the dust masses observed in these targets, predominantly by stardust production. But there are a few sources that seems to lie above, especially the ones with very low dust temperature. And in a recent paper by Marco Palla, a former postdoc in my team, we actually show that the James Webb metalicities are really crucial. So what we're showing here is the dust to stellar mass ratio as a function of stellar mass. So in the plot that I've shown you before, we're looking at the stellar mass versus dust mass. But here what we show, so the data points are the same here, it's only the model tracks that are very different. So these two model tracks have very different gas infall histories. And in this case, we're assuming that there's a total gas infall 15 times higher than the stellar mass. In this case, it's 3 times higher than the stellar mass. So in this case, you would have way lower metallicities. In this case, metallicities, gas phase metallicities would be way higher, because you have the same amount of stars produced. Yet these model tracks seem to both able to reproduce the trends here. So that shows that we have degeneracies and that we really need metallicity measurements to constrain the gas infall history of these targets. And luckily, we have some metallicity measurements that are on the way, and that show that there's relatively high metallicities. So there shouldn't be a lot of or not too much pristine gas infall, and that we're able to produce dust masses with high supernova dust yields and relatively efficient grain growth. Now, finally, I want to show some preliminary results also for the crystal survey. We've also recently been getting near-spec IFU data for 18 crystal galaxies. Now, the very interesting result, maybe you've seen it in the literature, what many people have found, so this is the diagram of oxygen abundance versus nitrogen over oxygen. Typically in the local universe, you see a bimodal trend. You see the flat curve here, where nitrogen over oxygen is purely, or nitrogen is purely produced by massive stars, oxygen as well, so you get a flat trend. But then here in this uprise, what you have is a contribution from secondary nitrogen production in low mass stars, where the CNO cycle is producing more nitrogen at the expense of oxygen and carbon, to see an uprise here. But of course, it takes some time for these low and intermediate mass stars, where the CNO cycle is active, to actually eject the material into the interstellar medium. Now, many high redshift galaxies showed very peculiar nitrogen over oxygen abundances, with many explanations that have been put forward to try to explain this. Well, it seems the crystal galaxies, only 1 gigayear of evolution and probably even less, they show, first of all, that they're heavily enriched with metals, but they seem to follow more or less the location here of the local galaxies, where the secondary nitrogen production seems to be important as well. So the next step that we're going to do is try to do some chemical evolution models to try and understand, okay, what can we learn more about the evolution and why do they seem to follow already the evolution of local galaxies and why is that different from other high redshift galaxies. We're also working on resolved dust to metal scaling relations, even resolved star formation rate C+ relations. So stay tuned for more results, and I'll leave you with my conclusions, hopefully shown you that James Webb has been really crucial in many areas, looking at galactic supernovas, supernova remnants. I didn't even have time to show you the Crab Nebula or supernova 1987, which is also really fabulous data. The fact that we can trace dust in these feedback-driven outflows and that it provides a way of tracing the cool material, dust destruction efficiencies, which remain unfortunately relatively high for now. The potential of lab experiments that show that maybe the grain surfaces are more reactive, which could provide a potential avenue for grain growth. And the upcoming studies now at high redshift, which are really unique laboratories because the timescales to form metals, to form dust grains are very short. So we really need to understand how that happens, and that can also shed more light on what we see in the local universe. Thank you very much.
Very much. Thank you very much, Ilse. I mean, that's just mind-boggling. I guess mind-boggling is the word, and many of us would just use this. I mean, the complexity and the richness of the physical processes. It's simply amazing. I will ask for questions, starting with students. If there are online people wanting to ask questions, please could you type in a question to the chat. So any students want to? Yep.
Thanks for the lovely talk. Very naive question here. I've heard that colliding wind binaries can also be dust producers. How do they, like say WR140, how does that factor into say like dust production versus destruction? Do they also destroy dust?
Colliding binaries or? Oh, I haven't investigated that at all. So
there's some like WR140, there was some really cool data from JWST last year. Like you can see the rings of dust.
Okay, so you mean Wolf-Rayet stars or? Yeah,
but in this case, in a colliding wind binary, I think that's
yeah.
important for producing the dust, but like, I'm not an expert in that.
Yeah. They're known dust producers for sure, but typically there are very few Wolf-Rayet stars. For now, we typically assume that they're maybe not so important, but especially looking at the high redshift galaxies, I think where there may be potentially more massive stars, I think it's something to reconsider for sure. Yeah, and it's beautiful to see the evidence indeed of dust formation there. Yeah, they're also, yeah. They could be potential dust producers, but I think mostly at high redshift. And should be, included in our model as well. It's a good comment.
Yep, dust production. Then we'll open questions to the wider audience. If you would like to also, yes, in the second row.
Thank you for the talk. I'm curious about the ALMA large program data where you see multiple peaks in one galaxy. I wonder if we also have rest frame optical or UV structures of them. And did you already briefly mention that they are usually offset, the clumpiness, the clumpy?
Yeah. Yes, indeed. We also have IFU data now from near spec, so we can also look at H alpha. And indeed, I mean, it's not in all cases, but for instance, in Rebels 25, which is more the high redshift source that I talked about, I don't have a figure to show, but indeed, what we typically see is that the dust is somewhat centrally located, and then we see some pockets of rest frame UV, optical, or line emission that is more around, centered around it. So I think that's an obvious case where the optical thickness of the dust is something that should be considered because that region seems to be so highly obscured, but that's not the case in other sources, or not in all sources, let's say. So I shouldn't generalize it.
Okay, there's Eduardo Bernados.
Thank you very much. Nice talk. I have a question on this one slide. So Rebels 25, this emissivity index of 2.5, is this completely unexpected? Is this a surprise? Or are there other galaxies like this in the local universe or cosmic noon like this? Is this 1 out of 40? Is the only one? Sorry, I have many questions about this one.
It's quite peculiar, but it's definitely not the only one. And the one thing, yeah, that we should mention here is that also we don't fully cover the peak of the dust SED yet, so that can also play a role. Plus, it's always, I mean, it's difficult to fully connect the dust emissivity index that you measure to dust properties because there's so many things. The broadness of your SCDP can play a role in constraining the dust emissivity index. So it's not necessarily, let's say, directly related to dust properties. We use it as a probe of dust properties. Sorry. Yeah, I don't know what I'm doing. I'm sorry.
And does this galaxy stand out by any other property, or do we expect to find more like this?
So the fact that this galaxy has a relatively low dust temperature, and there are other sources like that as well. So in that sense, it doesn't stand out, and I think we need to investigate whether that dust temperature is real, whether it is really so low, and why it is so low. It could also be that we're just that we're maybe now looking at the colder part of the dust SED, but that there's maybe a warmer component that we're not detecting yet, for instance. But it's not, I mean, even in the local universe, extreme cases also go to a beta of 2.5, but it is quite peculiar because typically it's between 1.5 and 2 is what we normally have for dust models as well, or just simple analytical modeling of these beta values. We fit a dust SED.
Okay, front row.
A different question. When people interpret the supernova 1A light curve data in terms of accelerated expansion, there's also a significant role of dust, intergalactic dust, and also dust in the host galaxy, as people like Kirchner emphasized very early. So how precisely is that dust correction to the accelerated expansion interpretation? How precisely is that known nowadays?
I must say that that's not really my field, so I don't know how. Yeah, I don't know how precise that correction would be.
I mean, this is slightly beyond your field of research, I believe. But
yes, yeah, I think in general we have a good
dust expert.
Yeah, I think in general in the Milky Way we have a pretty good idea of what the even 3D distribution. I mean, with the Gaia data, you also get like 3D. People have done 3D dust extinction maps to get an idea of where the dust is distributed. So even at higher resolution, which also makes it easier along a given line of sight to get a better dust correction. So I think definitely they have improved, but then beyond the galaxy, it becomes difficult because we're always assuming Milky Way-like dust, but we know if this is definitely not for sure. No, if you look at other galaxies, yeah, proper. I mean, already looking at dust extinction curves, looking at dust extinction curve, we see that SMC, LMC, and those are pure probes really of the grain size distribution and the dust properties, dust extinction curves, which we can derive. And we see that in the large and small Magellanic Clouds, it's already very different as well in M31. So we know dust properties are different, but it's very difficult to characterize purely on dust extinction curves. It's very difficult. We would need elemental abundances, I mean, from depletion studies to understand which type of grains there are. And even then it's really very degenerate.
Okay, question in the middle.
Thank you for the talk. I wanted to ask, so you mentioned grain growth quite a bit. Is there any chance, and by chance I mean in terms of the availability of data, for something like supernova 1987A to witness now, I mean, at least over the past 30 years or so, actually changes in the size distribution of grains there?
In 87A?
Yeah. Or others nearby?
Yes, but grain growth shouldn't take place, just to clarify, grain growth is mostly taking, or is supposed to take place in interstellar clouds, so not in supernova ejecta. But what we are seeing in I don't have a picture to show, but in 87A, For instance, they can compare Spitzer spectra with the James Webb spectra now in the mid-infrared, and then you see indeed a shift, which is probably showing that some of the smaller grains are being destroyed and that you get through the shock. And this is in the, I should say this is in the circumstellar ring that you have in 87A. So in there, due to the forward shock processing, you see that smaller grains are being destroyed. And that is likely a shift in the grain size distribution. That is something you can probe. But grain growth is very difficult to probe, especially because it's occurring in dense clouds, and then you have to separate coagulation, which is just different grains sticking together, but it's not a growth in mass. Or you really have accretion of gas phase elements, which also create growth of your dust grain, but both would give a sort of similar signature. So it's difficult to disentangle the two.
Okay. I think that's sort of another very interesting question. I mean, we wouldn't dream of asking such questions, you know, just a few years ago. I think the fact that you can ask the questions just shows you the progress. And it's wonderful that you've been able to give us a glimpse into this new world that's now developing. Before, I don't see any questions online, and I don't see any more questions here. I'm sure we all have more questions to ask further Ilse afterwards. But before we thank Ilse, I'd just like to make a couple of announcements. First of all, next week's curriculum. We're sort of, in a way, also looking a little bit from a completely different observational technique at the high redshift universe. But Carolina Henneke is going to tell us about some of the data analysis challenges and solutions to that next week in her colloquium here. And then on the next slide, to continue today's meetings, there will be drinks. Is it actually at Stefano? Is it actually at... So, okay, there will be drinks at students, so please meet up down here afterwards. And then afterwards, there will... Is dinner actually at Hemingway's? Dinner will be at Hemingway's. So come along at 7 o'clock. So, Ilse, thank you so much. That is an amazing thing that you've just showed us. And we thank you for your breadth of knowledge in all these different areas where you've been able to demonstrate some of the challenges and interesting new aspects thrown up with this data. I'm sure that maybe we'll invite you back in maybe a longer period, and then you'll be able to tell us the conclusions to all this, because this is one of those things where it's obviously ballooning up, and it's completely, I'm sure to all of us, completely fascinating and amazing that one can see this. So thank you, and thank you for your collaborators, but particularly thank you to you to coming and tell us about that at the beginning of this new year. Thank you.
It was a pleasure. Thank you.